Yeah. By then I'll just bring that. Alright, let's start. Alright, so the TAs, as you've noticed, have put up office hours. Okay. And office hours will happen in one of the TA classrooms. Does anyone not know where the TA office hours happen? Because they're the same set of rooms for all classes. So they are.
Where do they happen?
Okay, so yeah, so maybe they'll put up a room number quickly because we don't know the exact number. We know it's one of those two rooms, but we will find out and put that up. So they are basically right next to the CS, the main office of the CS department. Okay, so if you walk along the corridor, there are a couple of grad advisors, and it's the offices next to those. So I think even the board will say something to that effect, like TA rooms. But yeah, so this is something you can. So you might want to look into that. Yeah. Okay, so this is it, and also just so that all of you are aware, the course syllabus will contain things like video for the lecture, slides, and notes. Usually we might be about a day late in putting these up, but if it doesn't happen within a day, just send an email, just send a reminder and everything. Okay? So we'll try to do this soon after the lecture. And also some folks ask me for unannotated slides before the lecture, so I might I'll do it about half an hour before the start of the lecture. Okay? So because I usually tweak some stuff in the last one. Okay, so yeah, all right. So that's the course syllabus. And also, some of you signed up for Piazza, but I noticed that some haven't. So please do that as soon as possible. Okay. So you just have to go to this Piazza tab over here and just sign up. Okay. So in the last class, I mentioned a bunch of policies, but I forgot to mention the late policy for the homework. Okay, so the late policy is basically you can submit. Submit up to 48 hours late with 10% penalty. So homeworks will usually be due on Friday evening, Friday night. But if you guys can't make it, then you can submit until Sunday with a 10% penalty. Yeah. Yeah, let's just make it 10% penalty for the. But after the 48 hours, you cannot submit. Okay, so will not accept anything that's more than 48 hours late. Okay. Yeah, so this is, as you can see, reasonably flexible. So hopefully you guys won't have too many requests for extension. Okay. So that's that. And TA office hours have been announced. So please take a look. And I also forgot to announce my own office hours. They were on the web page, but I forgot to announce it. It is Tuesday and Thursday after class. So 1 hour after class. And from 1:30 to 2:30. If you prefer, yeah, I could also do slightly earlier. Does anyone prefer 1 to 2 over 1:30 to 2:30? Okay, good. So last year there used to be a database class that clashed with this, but this year there's no database. Alright, so that's that. And midterm, I didn't have any objections to it, so we will go ahead. It will be Thursday, October 3rd in class. Yeah.
We have a visualization class after this one. So
Okay. What time is it?
I think it ends at 1:45.
Oh, that's good then. Okay. So, yeah. Yeah, thanks for letting me know. Yeah, any other thoughts? Okay. Another thing is, as I said, if you want some feedback on grading and stuff, or on how well you write proofs, submit homeworks here. Alright, so these are logistics. And last class we also started doing a bit of examples of proofs by induction. And the basic thing we saw was bubble sort. So we wrote out the proof for bubble sort in full detail, right? And we showed a proof by induction. And you can also find it in the lecture notes. And we also, very roughly in the last 5 minutes, we had sketched out binary search. Okay, so this is something all of you had seen. So we just like very roughly went through it. And the problem here was you are given a sorted array of integers which is in memory, right? And you wanted to find if some integer x is in the array or not. Okay. And the idea behind binary search is to just say that you have this array which you know is sorted. And so, and this is an array of size n. And we said that you can very easily break the problem into a problem of half the size by just checking if the how the middle element compares with this query point x. Okay, so finding an integer, let's call the query x. So you compare this middle element with x. If it's equal to if this is equal to x, then of course you found x in the array. If it's smaller than x, then you know that x has to lie in this half. So you've essentially reduced the problem size by half by just doing one comparison. And this is a very simple example of a recursive algorithm. So you'll find the pseudocode and a more formal analysis of that in the lecture notes if you want to take it. But given that all of you said you had seen it last time, I've seen it earlier, so I'm not going to cover that in detail. And so another thing I would like to mention is, in general, the two examples we did last time illustrate what you will see throughout this course, what you should also be doing when you're writing up homework solutions and so on, which is you should follow the 3 steps. So first you should have an algorithm which you describe as pseudocode or something like this, and then you discuss the correctness, which you prove either by induction or by some formal mathematical argument, and then we analyze the running time. And in some examples, the last two will be involved with one another. Okay, so the process of proving correctness, or the other way around, the process of giving a bound on the running time may use the proof of correctness. So yeah, so that tends to happen. Right? So, but these are like the 3-step thing to keep. So any questions? Okay. So today we'll give a very short, like 1 lecture introduction to data structures. Okay, so this is a topic on which one can do an entire course if one wants, but we're just going to do some very basic things. And the goal is, I want you guys to know how to think about data structures. Okay, so that's the goal for today, and we'll do that with a bunch of examples. Alright, so the first question you should ask yourself when we're talking about data structures is, ultimately it's a way of storing the input. Right? So how does the way we store the input matter in algorithms? Okay, so that's the main problem in data structures. And we've already seen last time I gave, I was supposed to have a slide that says, so last class we also saw the example of how you store graphs. Versus matrix. Right, so if you remember, last class we said that if you have a graph, which is essentially a bunch of vertices that have some edges, we said that there are 2 ways you can think of storing it. One is as an adjacency list, in which for every vertex you maintain a list of all its neighbors. So that's one representation. The other is, if there are n vertices in the graph, you maintain an n by n matrix, where you put a 0 in an entry if there's an edge, if there's no edge, and you put a 1 if there's an edge. So you can store a graph either as an adjacency list or as a Boolean matrix. And we saw that for certain kinds of queries, one representation is better than the other. So can anyone recall what we had said? Like, what is an example of a query which is easier with a matrix than with a list? You want to find? Sorry. Yeah. Maybe.
If there's an S between two vertices.
Yeah. So if you're given two vertices I and j, and you're asked is there an edge between I and j, if you just had a list, you have to go through the list for I and see if j is in that list or not. But if you had a Boolean matrix, you just check if that entry was there. Okay, so that was a trivial example. And you can also think of cases where the list is better than the matrix. Right? So what would be an example where the list is better than a matrix? Sparse graph. Yeah, so in a sparse graph, a list is definitely more memory efficient than a matrix. Right? So but what about, let's say you're talking about time efficiency. Can you think of something where?
Well, if you just want to find all the edges of the vertex, then you just, in the adjacency list, you just go to the first index, whereas in the matrix, you have to go through.
Right. So a simple question like what are all the neighbors would take n time if you had just a matrix, and if you had a list, it would just take time proportional to the degree of that vertex, which could be way smaller in a sparse. And of course, also things like breadth first search and so on are much easier if you have a distance. Okay. So both have their advantages. Right? So that's what you should remember about data structures. So you have to think about what you want to do with the data. All right. So I wanted to give a couple of examples. So first one will illustrate a very simple data structure. And we'll start with what I call the Scrabble problem, okay, which is you're given a dictionary of strings, okay, S1, S2 up to Sn. You think of n as being pretty large, the whole dictionary. And let's say the average length is roughly L, and you're given many queries X, and you want to know if X is in the dictionary or not. So note that this is exactly like the binary search type thing, right? But it's just that we don't have a sorted array of numbers, we just have a collection of strings. So what is the trivial solution for this problem?
Compare each string to an array entry.
Right. So you know that there are the n strings, and so the brute force is for I going from 1 through n. Check if x equals si, and the amount of time this will take is roughly O of n times L, because I said that checking one thing takes one comparison takes roughly L times, because I said the average length is L, and there are n strings. So this is an obvious, this is a very simple problem. Okay. Okay, so now suppose you had to do multiple queries like this. Then is there a way of doing better? Is the question we'd like. So can you store the strings in a slightly clever way so that you optimize the query time? That is, when you get some X, you can very quickly tell if X is in the dictionary or not. So, yeah.
Let's do the hash table.
Yeah, so okay, so you can use a hash table, but then how you construct a hash table and so on will be questioned, right? So yeah, so let's say I wanted to do it from scratch. Let's say you had no idea what a hash table is for now. Okay. So how would you do it? Well, that's a good point. Yeah.
If that's not allowed on a binary search tree, like stored
Yeah.
automatically, for example.
Right, so you can always store, you can think of strings as the numbers in some sense, right? Like there's a natural ordering between strings, which is the lexicographic order. And you can just, this is what happens in a dictionary, right? Like you have words in alphabetical order. And now if a word you want to look up starts with some J, you will jump to J. Right? So that's the natural thing you would like to do. Okay, so here the idea is So this definitely works, right? But so you just have to first sort all these strings, and then you can look in terms of and then you can just do a binary search. And what is the running time of this procedure?
The sort of the search.
Right, so that's a good question, right? So you have to ask yourself, what is the pre-processing time and what is the actual query time? Okay, so the pre-processing time here would be, if you think about it a little bit, you can come up with something like n times L times log. So n log n due to the search, which is the number of comparisons, and L because each comparison takes roughly L times. So that's this is a heuristic kind of a computing. Yeah, I don't want to go into the details. Alright, so this is the pre-process, and the query will take roughly O of L times log, because you're still doing binary search, and this is what you want. So one question you can ask is, can I get rid of n altogether? Right? Like, can I store these strings in some way so that you don't even have like a log n dependence on the string? Right? So is there a good data structure that allows you to do? Is the question clear? Yeah, we'll come to the answers in a bit, but is the question clear to everyone? All right. So yeah, maybe we'll start with you and I'll go to the next one. Yeah.
I can't remember the name of the tree for the life of me, but if you store a tree where the nodes are the letters of words, and then you, as you're clicking these words in, you just start with the first letter, so on and so forth, go down, and then you can just search through this tree with your query.
Excellent. Okay. So that's great, right? Actually, this is the kind of understanding I'd like you guys to have. You don't need to remember the names of these things, just remember roughly what the idea behind these things is. So did you have the same answer?
I was going to say we get rid of the n involved at all if we use like a hash table.
Right, but yeah, so hashing has some subtleties that usually people don't talk about, but we'll come to that later. Okay, so that's why I've been avoiding discussion of hashes. Okay, we'll come to that in a little while. But what he said is a perfectly good solution that that we will look at. Okay, so what he's saying is, he's describing a data structure that, and ultimately, so the question is, yeah, so we want to store a bunch of strings, right? So what he's describing is a data structure where you store the main idea is storing strings in a tree. Okay. And roughly speaking, like if you think of strings as just having characters that are A through Z, let's say, for simplicity. So then what you can think of is, suppose I want to represent the word, let's say, cat. So I can think of first having a node for the empty string. And it can have descendants that correspond to, like there's a descendant corresponding to A, B, C, so on, to Z. And if I want to store, if I want to look for cat, then I can imagine going through here, and then C will have a descendant which corresponds to A. Then I can go down here, then I can go down to the neighbor corresponding to B. So this is a rough idea that he's trying to suggest, right? Which is, in some sense, store strings as every string can now be thought of as a vertex in this tree. Okay? So you don't have to explicitly, in principle, you could think of it as an infinite tree, right? Where you just have 26 descendants for every node. But you don't have to store this infinite size object. Every word you have is one node in this tree. Okay, so every string you have is some node in this tree, right? So if I ask you what this node is, what would be this node? What would be the string corresponding to this node? It's CZ, Right? So this is the string C that. Okay. So if you prefer, you can think of this as yeah. So is that every string corresponds and this sort of a data structure for storing strings. So this is called two words for it. One is a prefix tree, or people also call them tries. So I don't know why they call it a trie, but yeah. So it's prefix tree makes a lot of sense, right? Because it's yeah, in some sense the parents of a node. Like if I look at this node, it would be a prefix of the string, right? This node corresponds to CA. This node corresponds to CAT, right? So it's like if you go up in the tree, then you get a prefix of the string. That's why it's called prefix. So, all right. So I just described the prefix tree. Now, how do you store a collection of strings? Yeah.
So I think even so we take data structure. Now the complexity is OL, right?
If you want to, yeah, we'll get to that in a little bit. Yeah.
So I think we can also reduce this to O1 if we are able to do parallel search.
Right. Yeah.
Means that we have a word, and if we are able to compare each of the character one by one, but all of them in parallel form, then we can do search in O1.
Well, you have to be careful because you don't know where to look, but we'll come to that in a little while. Okay, so first let's see the O of L to start with, and then we'll get it. Okay, so the first idea is how do we now store a set of strings, right? So I showed you that every string corresponds to some node in this tree. Okay. So how do we now store a set of strings, sorry. Right? Like you had a dictionary which consisted of S1, S2 up to Sn. Now, how do you store this whole set of strings?
You're already storing CAT and CZ. So we'll, like in the last slide.
Right. So I mean, if you think about it, I mean every string is there already in this tree, right? It's just that you have to have some special marker that says that, oh, this is actually a word in my dictionary. Okay? So think of having like a checkbox or something at every point. So just like one additional Boolean variable that says, oh, is this actually a word in my dictionary? Right? So you have the same tree, and you also have a Boolean that says, is this a word? Yeah.
Would that mean that AT is also a word?
No, so yeah, we'll come to that in a second. Yeah, because you only put a check mark here. So I'm not asking you for check marks along this in this path. Like if I had to conclude that AT is a word, then I would have put a check mark in this box. Okay, so here there will be none. Okay, so you cannot conclude that AT is a word from the fact that cat is a word. Right? In general, that's not true. It just so happens in this example that that's true. Yeah, but that's a good point. Yeah.
Is this better than like having a specific character like this name? So like instead of having 26 characters, you have 27 and have the extra character be like the end word.
Right. Yeah, so that's an implementation detail. Yes, you can do that. And you can have it as null or something if it's not there. Yeah, you can do all these sort of things. It's just, yeah, it's conceptually it's just easier to think of having a Boolean. Yeah.
So what if we have cat instead of cat?
Right. So if your dictionary had both cat and cats, then what would you do? Anybody else? Yeah.
Just add s.
Right. So you now go further in the tree, add an s, and put a check mark here as well. Okay. And that's a nice thing, right? So every vertex corresponds to some string, and to check if that is a word or not, you just read off the boolean for that. Okay? And cats is this vertex. Okay? And if there's a check mark there, it means cats is in the dictionary. And if not, it is not there. So we are not trying to come up with any general rule like, oh, if bat is a word, bats is a word kind of thing, right? Because that's beyond the scope. We just want to know if it's there in our set of strings. Okay, so yeah.
And you don't even need a full tree for this.
Exactly. So that's the next subtlety that I would like to mention, which is even though conceptually this is an infinite tree, you don't have to keep track of the whole infinite tree because you just keep track of things if you keep track of a node if there's some descendant of it that is actually a string. Okay, so this won't be an infinite thing or anything bad like that.
So I guess it will probably be easier to think of the words as paths instead of the
Yes.
words.
So yeah. So this depends on your point of view. So for me, a vertex is if you have a tree, a vertex is like a path because the path from the root there's a unique path from the root. But yeah, so if you find it easier, feel free to think of it as
So I was just thinking we can have a Boolean flag at every like you have here, which tells us if the word terminates there or not. So
Right, exactly. Yeah, so which is the same thing. Yeah, so that's another way to think. All right. So good. So this is how we store a set of strings. Right? So I'm not going to write the pseudocode for this because I hope everyone has followed the procedure. So it is. For the SI, we mark the corresponding vertex of the tree as true. By default, everyone started off with false. So this is how you store a set of strings in this tree. So now, as you were saying, what is the query time? Okay. So if I'm given an x, that is given an x. How long does it take? If x belongs to this set S. Okay, so S, let's say, is this capital S set of strings. Okay, so how long does it take? Order L, and assume that it's clear to everybody because you just the way we store things is let's say x is I don't know, ATS. Okay. So then you start at the root, go to A, go to T, go to S, and if there is no S, if there's no neighbor here, that means that the word doesn't exist. Okay. There is an S, but there is no tick mark here, then it means that the word is not there anymore. Okay, so that's how you check. So the algorithm is just using characters and if we encounter empty tree, return no. Or else, if we don't encounter an empty tree, it means that we went all the way down to x. And then otherwise return the boolean corresponding to x. So x will correspond to some node. Return the boolean of that. Okay, so this is a simple application, and this takes time O of n. Okay, so querying is fast, And also time taken to build the data structure. So how much time are you taking to build the data structure? Building the data structure just means adding all the words, right? So in some sense, we're just asking how long does it take to add one word? Yes, that's what we can ask, right? So how long does it take to add a string? Yeah.
Would be S times L. Well,
Size, yeah.
L for one string.
Right. So for every string, you can also add and remove the string in O of L time, because all you have to do is go down the tree, and if there is no descendant, then you make a descendant, and eventually you go down the path, and then you mark it as true. Okay? So the algorithm is simply the add procedure is, let's say, add of some string, not call it x, let's call it y. So the way it would work is go down the tree, following characters of y, and making nodes if necessary. Actually, does everyone follow what I mean by this making nodes if necessary? Remember, I said I don't want to store the whole infinite tree, right? So it's like only building the tree if I need it. Right? So that's what I mean by making nodes if needed. To implement these things, you need pointers and stuff, but it's conceptually very easy. And then just put set boolean corresponding to y to be true. So this is very clean. So it's and removing a tree if you want to be lazy is also very trivial. Just you go down the tree and you set the boolean to be false. You may want to be careful and occasionally clear out all the junk that, like you may have built a huge tree which you don't need. But if you don't care about that, if you don't care about garbage collection in the end, you can just set that boolean to false and be done. So both of these operations just take O of L time. For adding length and adding length. Okay, so good. So everything clear so far? Alright. So this is a very clean procedure, and if you do this for n strings, so yeah, so let's do this. Actually, before that, let me answer the question that I asked to start with. I asked you how long does it take to build the whole dictionary, right? So earlier, pre-processing took this much time, even if you used a binary search tree. Okay? And query time was something like this. And now if you're using prefix trees, so using prefix trees, this becomes O of n. Okay, so the log n is basically gone, and there's no sorting or anything like that needed. And this query time is just O of n. Okay, so this is the advantage you get from using these. So it turns out that this is a pretty popular way of storing strings. Okay, so that's why I'm covering this, and it's quite succinct, because if you think about it, if you have lots of words, presumably they'll share a lot of these prefixes, and so the amount of memory you need just becomes basically this extra boolean that you've got to store for every word. Okay, so it's actually a relatively small amount. So these are called prefix trees. All right. So let me conclude with with this slide, which is trivial for this data structure, but the reason I'm doing it so explicitly is because all data structures should just be abstracted out like this. Okay? And think of it as an API if you'd like to. Right? So any data structure, what you've got to ask yourself is, actually I forgot one point, which is what is being stored. Okay, so in this case it was here, so what is being stored was just sets of strings. Okay, and what are the operations that are supported and how long does each operation take? So those are the things you should be asking when you talk about data structure. So these prefix trees store sets of strings, and you allow things like adding a string, remove, and query. And each one takes time of time. Okay. And I also added a comment that this could also be a poor man's binary search tree. What do I mean by this? Like, what do we use a binary search tree for? It's for storing integers, right? And if you had integers that are all of that all had some n bits in them, or L bits in them, if you had L bit integers, note that L is very small, right? Usually a computer's memory, they're all 64-bit integers. So 64 is pretty small numbers. So if you had L-bit integers, then you can build such a tree, and now you have L time, query time, and so on. Okay? So if you had lots of such integers, then this is actually a pretty simple implementation. So it's not quite a binary search tree. If you guys have implemented binary search trees, you know that it can be somewhat messy. You have to do some rotations to keep it balanced and so on. Okay? So here there's nothing complicated, right? It's just you're adding things to go along. So if you really wanted a hacky implementation of a binary search tree, this would actually be a reasonable one. Okay? So in practice. So just can treat them as strings. And use these tries. Okay. So, all right. So it's just a comment. The other thing, maybe I would, since we have time, is maybe address what he was saying. So sometimes you can think of trying to do these things in parallel. Okay, so if you had like multi-core processors, if you had to search for a string, maybe you don't want to like go through the tree one by one. Maybe you want to do some parallel searches. Okay, so that turns out to be somewhat tricky because you don't know how exactly to, like, suppose I'm looking for the word X going from, let's think of a big word. Okay, so what is a big word starting with CA? California. Okay, so yeah, so if you had a big word starting with something, you might start off some procedure over here or some procedure over here, something like this, and okay, or you might be able to memorize certain small sets of strings. You might only start searching from there as well. Okay, so there are some hacks you can try to do, but in general, this is non-trivial to do. Okay. Did you have any specific procedure in mind?
So in hardware, I know because there is a CAN structure
that
you can see.
Okay. Yeah. So things like this are good for you guys to think about. See if there's some clever things you can do if you have multiple cores, right? Like 10 different cores be working on different parts of the memory. Okay. But in general, yeah. So they're a little bit out of the scope for this class, so I won't do too much of them. Yeah, but that's an interesting thought. Okay, so the second example I'd like to do, maybe some of you have seen this, is it's one of these canonical web search examples, right? So what is web search? You're given a bunch of documents. Not talking about the ranking problem here. Let's just want a list of web pages that contain a certain set of words. So you are given a huge corpus of documents, a huge set of documents, okay? And so let's say there are n documents where n is large. N is, think of it as, about 10 to the 9 or something. Okay, so it's a pretty large number. You can't, usually you would not want to iterate over this. Okay? So you have this, but every document contains a fair number of words, but not too many. Right? So list of words of, let's say it has m words. Think of m as a few hundred. So let's think of it as 100 to be simple. Okay. And now your question is, you're given a collection, a set of words. So suppose I give you a set of words, let's call it board or and last. And I ask you to find all the documents that contain both these words. Okay. So if you just stored these documents as they are, so what would be the most basic solution?
Linear search.
Yeah, so you have to go through each document, and you've got to find out, oh, okay, does it contain sport, does it contain Alaska, and so it is definitely much more than n type. Okay, so this is, as you can see, this can be pretty, I mean, this would definitely be very inefficient. So because, so it's n times m at least. Okay, so let's, we can even write that. More than n times. But we already have some intuition that most words don't occur in most documents. Because every document just contains like a few, let's say 100 words, and there are about 100,000 words in the dictionary. Okay, so every document contains only a small set of words. So can you use this to come up with a smarter way to, so can you store your collection of documents in a smarter way so that you can answer these queries better? Yeah.
So we can do something like hashing that basically stores two things. First is that if that word happens in that document, and if it happens, what is the index of the word? For example, the first word, second word, third word, kind of thing.
So just to be sure, let me call these words as Q1 up to some. Let's assume for simplicity that there's only two words. Okay, so as queries, so Q1. What you're suggesting is for each document, you want to build a structure that will allow you to very quickly tell if Q1 shows up in the document or not. So that's fine, but that still has the n in it, right? Because you still have to go through each document. Okay. So is there a, yeah?
Why don't we just have n point at n instead of vice versa? So we'll have the words point at our documents.
Okay.
The other way around.
Exactly. Okay. So this is called this notion of an inverted index. Okay, which is this is what you see in textbooks, right? In the end, you'll have this. Forget what it's called. Yeah, gloss or something like this, where it's where you, for every like concept, you have a list of page numbers in which it shows up. So the idea is to do the same kind of a thing, and this is called the inverted index, which is for each word. Store the list of documents it is present. Okay, and now you have the list for Q1, you have the list for Q2. Just take the intersection, and that's all you want. So now if we are given query, given Q1, Q2. Okay. Of let's call this now you just have a set intersection. So if both of these are relatively small compared to capital N, then you have a pretty great procedure, because now you avoid taking n time. Okay, so this is something that's commonly done. Yeah.
But the pre-processing time will be huge, right? For
Yeah. So I want to get to that. Yeah. So right. So here, but if you think about it, okay, so let's see what the pre-processing time is. Yeah. Okay. So what is running time? As you know, it's pre-process time plus query time. So what is the pre-processing time here? You have to build this inverted index, right? So you can imagine having a preformed an empty list for every word, and now you go through the documents. For every word, you add it to that list if that word is an document. Okay. So if you think about it a little bit, so this takes time, which is O of n times. You have to go through each word. There's also terms that depend on the length of the string and so on, which I'm ignoring for now. I'm thinking of those as constants. Alright, so this is the pre-process time. And query time, it depends on the words. So there could be some super common words like the or something, and then those would occur in a huge number of documents. But if you ignore that, it's typically its size of the inverted index, size of inverted index of the query word. So something like this is the query time. Okay, so plus, if you really want to be worst case, then it's plus size of inverted index of Q2 and so on. So this is roughly the time you take, and this could in principle be much smaller than that. And in practice, there are a lot of optimizations you can do to store sets in a clever way and so on. Okay, so people can figure out ways of doing this really quickly. Yeah.
Wouldn't this make searching for a list of words in a particular document more difficult? Like, is there a certain data structure that can make it easier to do both of those things, like searching for a certain list of words in a document as well as searching for documents which contain certain words?
Right. Yeah. So people usually build this and store it in addition to the documents themselves. It's not like you only keep the state structure, right? So yeah. So people have store the documents. I mean, that's the corpus which is there, and you also have this inverted index, which you use only for the purpose of query. Okay. But what I would like to say is that the pre-processing time is not terrible. It's just the amount of time needed to find the corpus to like get the corpus in the first place. Right? Because these are n documents each having m words, so just like storing all of these, getting them to one place takes roughly this time. Okay. So it's not too much overhead compared to how much time you're already spending. So this is big, but not. Not there. So there are some examples of data structures where if you spend much more time, you can do way better. Okay, so we may not have time to see examples of those, but yeah. But this is not one of those. Okay, so here both are somewhat easy. Yeah.
You mentioned that in the live approach, it would take more than n.
Yes.
How would that be?
Oh, you mean why is it more? Why is it not equal to n times n? Oh, I just meant that in each document you have to figure out if each of the words is present. So I don't know, naively, how would you do? Yeah, so maybe it takes 2 times that if there are 2 words or something like that. So, yeah, that's all I meant, but it's at least this. Okay. Good. So there was another question. Okay. All right. So this is one example where storing things carefully could potentially save a lot of time. All right. Okay, so the final example I would like to give about data structures is this notion of dynamic arrays. All of you must have seen examples of dynamic arrays, but I would just like to point out one interesting fact that maybe not all of you have thought about, which is, yeah, how many of you have thought about how dynamic arrays are implemented? And just to be sure, dynamic array is just one where you don't pre-specify the size. You just you have an array and you keep adding elements, deleting elements, whatever. Right? So you can delete the last element, and you can add a new element to this list. Okay, so it's some kind of a dynamic list is probably a better word for it. But it's an array in the sense that you should also be able to return ith element. I forgot that this is the main reason we call it an array. Right? You should have random access. Okay, like otherwise this can be done in a list, in a queue or something. But you should be able to very quickly return the ith element given a number. So, right, I mean, if you think about it, an array has to, if you're declaring an array with a specific size, what the program does is it makes a certain amount of memory available, right? So, and you have to do that if you want random access, right? And so now how can you do this without actually knowing what in advance what the size is? What do you mean? Oh, who said pointer? Okay, yeah, sorry. Yeah.
So in pointers, we don't really have the whole thing defined. You keep just adding to the address and you keep storing value into it. So it's dynamic array.
Okay, so what she's suggesting is you keep creating a list like this where you know what the next element is. Presumably you know what the previous element is, and so on. And you keep track of a list like this, right? And this would create a dynamic array, sure. But what if I want the ith element, right? So you don't know where the where the ith element is, right? So that's and you would like the ith element in constant time. Yeah.
Back with the traditional array, and then once it gets too big.
Right, then you have a chicken and egg problem, right? Because are you suggesting that you store the index of this ith thing in a traditional array?
I think he means for the structure in general. Just use an array and then resize it.
Right. Okay. So what he's suggesting is, okay, so use an array and you try to resize it carefully. But now the question becomes, what is the original size you declare for the array? And how do you resize it and when do you resize it? Right? Yeah.
Well, if I'm thinking about it correctly, in C++, when you create a dynamic array of a certain size and then you reach that certain size, what it'll actually do behind the scenes is create a new array, copy over all the values of twice that size.
Exactly. Okay, so that's what I would like to get at. Okay, so the way these things are done, which is interesting, is okay. So I need this. Yeah, the main idea is start with a certain size. Let's say you start with some default array size, it's like 20 or something. Okay, so it is respectable but not too big kind of a size. And so start with some reasonable size. If you reach the limit, initialize array of double the size and copy over. Okay, so there was a hand here check. Yeah.
Does the add operation always add to the end?
Yes. Okay. Yes. Right. So the operations I would like to support, this is what I was saying, is I would like to have add to the end, delete from the end, and return the ith element. So this is what the C++ vector, for example, is. Okay. And right, but now if you think about it, right, so what it's doing is, if you reach the limit, then you're actually initializing a new array of, and let's say your current array size was something like n, small n. Right? Now it's actually now initializing an array of size 2 times n, and it's copying over all the elements. And this takes time O of n. Clearly, it takes time 2n in particular, because it's initializing something and then it's copying over n. So, but isn't that a problem? Because we want all of these operations to run in just for one time. Yeah.
So you don't do that every time you add.
Right, exactly. Okay, so that's precisely the point, right? Which is that we do it only if your size exceeds, if you reach the limit, then you double the size. Okay? So the next time you're going to increase the size is after you've added n more elements. Yeah, that's a lot of elements, right? So that's the idea behind what is called amortization. Okay, so amortization is a word which technically it means apparently killing off slowly. Like mort is the Latin root for death, I guess. Yeah. So, but yeah, what it means is, so it's something that originated in the context of loans and stuff, where you like finish it off slowly. Yeah. Okay. So, but this is a powerful idea in analysis. Okay, which is some operations can take a lot of time. Okay, like if like sometimes adding an element can actually take n amount of time. Okay. But the point is that if you just add elements, this happens very rarely. Okay, and this is a point. And the notion of amortized analysis, so this is what I've written here is a pretty strong one, and you can actually ensure it in the context of our operations. But if you only think of adding, this becomes easy to prove. Okay, so what I'm saying is, some operations can take a lot of time, but if you average the amount of time over any n operations, it still takes the total amount of time is still O of n. Okay, so this is not the average, but total time for any n operations, n consecutive operations, is only O of n. Okay, and this is exactly what she observed. So she said that you go from, let's say your initial size equals n0, and if you only considered add operations, let's only consider add operations. So until you hit a size of n0, clearly it's just one element you're adding, and then you will double. So you'll become new size will become 2 times n0, and now you can go for n0 more operations before you then double. So now you can do 2n0 more operations. Right? So if you think about it, the total number of operations for n total for adding n elements is roughly 2n. Because each time only at these specific intervals, if you think of n0 as 1 for simplicity, then only at powers of 2 you will do some lot of work. But the total amount of time will be powered. Okay, so this will be small constant times L. Right? So this is roughly the analysis. Okay. And the reason for this, the reason why this all works is that if you had numbers like 1 plus 2, like some 2 to the r, then this sum is only 2 to the r plus 1, right? So minus 1. So this is roughly 2 times 2 to the r. So okay, so if you added this, this is just a sum of a geometric series, right? So only the last term matters in some sense. Okay. So that's the reason I'm saying that the total time for adding n elements is only 2 times. Okay. So yeah, I will pause here for a few minutes, and if you have thoughts, questions.
For the try, we were having the pre-processing time.
Yes.
Yes, it was n into L. Would that also be called the amortized time? Because L was the average length of it.
No, so that is a pre-processing time. It's usually quite different. So here there is no pre-processing. Here it's just a dynamic array where you are building the array.
Right. So I'm asking if the time would be called amortized.
No, it amortized makes sense only in the context of a collection of queries. So there we did not talk about amortized time because we could actually bound the worst case time by L. Right? We said that every operation takes at most L time. Right? But here we are saying some operations can take a lot of time. Right? But on average, if you averaged over n operations, you take only n over n time.
Right. So the average length of the string was L, right?
Right. But the L is string, it's still one string. That's the point. It's not like a collection of strings. Yeah.
So what we can do is that before reaching to that limit that we have, we can basically overlap building the new data structure with what we previously were doing. So in that case, we can find all the timing operations that required for building.
Right. So what he's suggesting is maybe you don't have to like really double only at the very end when you reach the limit. Maybe you can plan ahead, right? So you could say that suppose my current capacity is n0 and I'm at n0 by 2 or something. Then I could say, okay, I'm going to plan ahead. I'm going to anyway create a new array. If I add one element, each time I'm going to add like some 2 of the previous ones into this array. So this way I can really make sure that every time step takes almost the same amount of time. The reason that's not done is because adding is not the only thing we care about. We also care about like subtracting and stuff, and also the total amount of work done is the same anyway. So it doesn't matter too much to do these things that carefully. Okay? Because you assume that you care about the running time of the whole program, not about the running time of each individual operation. Okay? So it's just in these modern applications that we care really about the time of individual operations, right? Like maybe person makes an update to an array, maybe there's a distributed array and one process makes update, and there you care about each one having a small latency. Right? But in traditional applications, you would have one core doing all these things, and so you wouldn't really care. Okay? But these kind of things are good to think about. Okay? Can you just really make sure every operation is small? So another question that you should be asking is, how do I now do deletion? Right? Like, if I don't do garbage collection, then if I add a lot of elements and delete all of them, then the size of the array is now really big. The amount of space it's using is huge. Right? So, any thoughts?
Yeah, deletion should be actually simpler than adding because if say we use this ratio of 2, once our array is less than half full, we don't actually have to copy to a new array. We can just deallocate the back half and keep moving.
Okay. So what he's suggesting is, so deletion should be easy because forgot I had slides for adding. But never mind. So the moving idea one is if array size or rather if half the allocated space is unoccupied, okay, then deallocate the latter half. Okay, so what that intuitively means is that we have this allocated space, and we've used something until here, and half of the stuff is left over and it's empty space. Okay. Then you can just deallocate them. So this almost works. There's one subtle issue with it. Can you guys think of? Yeah.
If we do an add right after this, we're gonna immediately roll that space back. So if we delete, can we delete that last half of the array? We're immediately gonna, when we add after that, we're immediately gonna want to.
Yeah, so you run into these issues that somebody could then say, oh, I'll add and keep deleting, right? So I'll add one element, delete one element. And now if you are here and you add, then now you have to create a new array and copy that into that, right? And then you delete, and then you realize that, oh, half my space is unutilized, and you remove that. So now you're taking n time for each operation. So that's bad, but it turns out you can get over this with a very simple hack, which is you remove this latter half only if you go below like a fourth. So when you go under a fourth, don't delete all of the space, but delete just the half, so that you still keep a half. And that way you avoid these kind of bad cases. Then you can actually formally prove that this doesn't. But yeah, so we won't do that because it's just computationally messy. Yeah.
For each division, is this still going? Is this right?
Sorry?
For each division, it's still going?
No. So each deletion, yeah, so I haven't talked about how you actually implement deletion, right? I'm only asking you to delete the last element. That's the only operation I'm supporting, right? So if you delete the last element, you can just keep track of a pointer that says, or an index, which is how many elements does the array currently have. You reduce that by 1. So, and that's all you do. Okay, so everything is constant time. Yeah, but that's a good question.
Yeah, in this example, do we assume deallocating memory is a constant operation? Or is it?
So it depends. I would like to assume it is constant, but yeah, some people might say it's not. Yeah, I don't know. Yeah. I mean, but it doesn't matter. Even if it takes n, this analysis will still work. Yeah. All right. So this doesn't quite work. And the reason is the add example. Okay. But if you modify it slightly, which is that if 3/4 allocated space the last half. You still deallocate only the last half, but you do it only if you really need to. Allow yourself some slack. Alright, so this is how dynamic arrays are implemented. Okay, so it's just and the point I'd like to make is that sometimes we cannot ensure that every operation takes a small amount of time, but if you are careful, you can ensure that on average you're doing pretty well. So the total time for any n operations is on your side. Okay, so good. So I think we have ended early. But before that, I'd like to just do a quick recap. Okay, so whenever you think of data structures, in some sense, the details of the data structure, how you implement it, are somewhat secondary. But what you should be asking yourself is, what elements are being stored? What is being stored in the data structure? Okay, so this is the first thing you should be asking, and then you have to think about what operations should be supported. This is if you are implementing the data structure. Otherwise, you just have to know what operations are supported. Okay. And the complexity of each operation is something you would like to understand. And of course, the total size of creating of the data structure itself, how much time you take to build it, and so on. Okay. So these are the sort of things you should be asking. In any data structure, you can just abstract it into this, and that's how you should remember. Okay. So things that you might have encountered. So I just want to give some examples of. Some of them are not too fancy. Like the first line, they're all somewhat standard data structures, which some of you might have seen in undergrad courses, which is things like priority queues, heaps, and so on. Union find is a very cool data structure, but we don't have time. Okay, so that's so these are some examples. And hash tables are something we'll get to when we cover probabilistic randomized algorithms. Okay, so these another very popular choice of data structure. This we'll probably not get to in this course, which is locality sensitive hashes. How many of you have seen or heard of? Okay, so this is something that it's a very powerful tool in doing what is called nearest neighbor search. Okay, so you have a bunch of points, and you're given a new query point, and you ask what is the closest in your database. Okay, so your database consists of a bunch of points, and which are in some geometric space. Now you're given a new point, and you ask what is the closest one. So this is used in like face recognition and software like this, because the database has a collection of faces, and you want the closest face to a given face. So there's lots of applications for this. And here you can avoid actually searching over the whole database in some clever way. Okay, and this is called a locality sensitive hash. And so yeah, and this is the example I was thinking of, where pre-processing time is actually much larger. Pre-processing can be expensive. I mean, it's more expensive than you would think. And but searching then becomes easy. So there's a trade-off between how much time you spend pre-processing versus the advantage you get at the end. So there are some nice properties like this. Okay. All right. So let's end here. So next class I will talk about divide and conquer algorithms with a bunch of examples.